We are here to help.
In Part 1 and 2, we explained how to recognize and solve exact differential equations. Now we are going to explain what to do when a differential equation is not exact, but can be transformed into one. As we saw in Part 1, if the following equation does not hold, then the differential equation is not exact. In this case, it is sometimes possible to find an integrating factor mu. When we multiply mu with our differential equation, it becomes exact. Unfortunately, there is no general approach to finding an integrating factor, but there are a few rules of thumb we can follow. If the following expression is a function of x only, then we use the integrating factor e to the integral of f dx. We will call this scenario case 1. Let's look at how this integrating factor works through an example. When we check for exactness, we find that m and n's partial derivatives are not equal. So we check the criteria for case 1. This expression should be a function of x only after it's simplified. As we can see, our result is a function of x. Now we can plug 1 over x into the equation for the integrating factor. We get that mu of x is the function x. Now we multiply the original differential equation by our integrating factor x. We can see now that the functions m and n are different. And when we check for exactness, the condition is now satisfied. Now that the original equation has been transformed into an exact differential equation, it can be solved using either of the techniques explained in parts 1 and 2. There are a few other special cases where we can obtain integrating factors by checking a condition. If the following expression is a function of y only, then our integrating factor is e to the integral of f dy. If this expression is a function of xy, then by making a simple change of variable, we can rewrite our function f of xy in terms of z, which allows us to easily calculate our integrating factor in terms of z first, and then substitute back in terms of xy. If this expression is a function of x squared plus y squared, then by making a change of variable, we can calculate our integrating factor in terms of z, and then substitute back in terms of x squared plus y squared. If this expression is a function of x over y, then if we let x over y be z, we can make a change of variable, calculate our integrating factor, and then change back in terms of x over y. These 5 cases are not the only ones that exist. If you find another integrating factor that works for the equation you are solving, that is also okay.